Okay, now we're going to look at the problem in Serway and Jewett in Chapter 7. We're going to look at number 63 and number 64, which is basically the same problem. We're going to do them both at the same time. So the problem tells us we have an inclined plane, angle of 20 degrees, has a spring force of constant 500 newtons per meter. It gives us a mass of 2.5 kilograms. It says we slide, so the mass is 2.5 kilograms. We slide a distance, this distance here, d down the incline, right, and that's a distance of 0.3 meters, and it's shoved down the incline. So we start with initial speed v, and it's pushed down the incline with 0.75 meters per second of velocity. So then the question asks us, by what distance is the spring compressed when the block momentarily comes to rest, right? So it asks us what this distance is here, because it smushes the spring down, it compresses it by this distance x, right? Eventually it's going to come to rest, and then the spring will push it back up. But how far does it push the spring in before it comes to rest? So the unknown that we're looking for in this problem, what we really need, is to find x. So how do we find x? Well, we need to categorize this problem. What type of a problem is this? Is it kinematics? Is it a momentum problem? Well, if we look at the system, right, we have a spring in the system, we have an object changing heights and speeds. The fact that there's springs and spring constants and that we're looking for the distance a spring is compressed leads us to think that hopefully conservation of energy is the idea. So just that the initial energy we start with at the top of the hill is going to be equal to the final energy that we end with when we get down to the bottom. So this is a conservation of mechanical energy problem. We have an isolated system consisting of the mass that's sliding, the earth because of the gravitational involvement, and the spring itself. So now we're ready to analyze the system. If we take a look at what types of energy we have at the beginning, we know that we have some kinetic energy because we're being pushed down the hill. We know we have some initial gravitational potential energy. Right? At this point we have to be careful. Let's define our 0 point. And for reasons that hopefully become clear, I'm going to say our 0 point is at the point where we make contact with the spring. So this is going to be height equals 0. The uncompressed height of the spring. At the end, then, we'll also have gravitational potential energy because we're going to be below the level of the spring. We're going to be below the level of the spring by this much. And that'll be our height final. Whereas, of course, our height initial is this height. And of course, we'll have our elastic potential energy left over at the end as well. So if we break that down further, you see we have 1/2 mv initial squared plus mg d sine theta is what we get for the height of when we use trig. We see that our initial height is just d sine theta, right? Of course, and our final height is negative, right? Because we're below 0, negative x sine theta. So we have minus mgx sine theta, and then of course plus 1/2 kx squared on the other side of the equation there. You can try all you want to go ahead and solve that without using a quadratic equation, but you're probably not going to be successful. Once you reorder this, we have 1/2 kx squared minus mg sine theta x minus this other stuff equals 0. Now I know that I'm going to have to use the quadratic equation to solve for x, because I've got an x squared and an x, and I can't really do anything about that. Try as you might, you're going to have to use the quadratic equation, which I definitely didn't have to look up and knew right off the top of my head. is minus b plus or minus square root of b squared minus 4ac over 2a, right? If it's in the standard form, ax squared plus bx plus c equals 0. Right? We have our a is 1/2 kx squared, b is minus mg sine theta, c is minus the whole quantity, negative 1/2 mvi squared plus mgd sine theta. We use the quadratic formula and we get the magic number, which is actually going to be the solution to problem 64, because this will be our x without any numbers in it. So mg sine theta plus or minus, that's our minus b, plus or minus square root of b squared, so that's m squared g squared sine squared theta minus 4ac, which, well, 4a is just 2k, so that's going to be, distributing that through c, we'll get a plus k m vi squared plus 2k mg d sine theta, and all that over what, 2a, so that's just over k. Right, and that's basically our answer. If we're looking at the second problem, problem 64, which just asks us for the symbolic answer for x, we could probably simplify that somehow, but probably not too much. So let's just leave it like that. Of course, if we put in numbers, we get mg sine theta is 8.379. That squared is 70.216. Km v initial squared is 703.125. 2 kmg d sine theta is 2513.7. So when we do all that out and we plug in for our numbers, we get x is going to equal 8.379 plus or minus 57.33 all over 500. Just k. So all over 500. That's going to give us, well, two answers. And if you get 0.131 meters or negative 0.098 meters. Well, physically, x isn't going to be negative. We know that x is going to be pushed in and not pulled out. That would be corresponds to an unrealistic Hooke's law, where the force is in the same direction as the displacement. So we know it's not that one. This is our answer. The spring is compressed 0.131 meters, given the numbers above. We want to finalize our answer, check that it makes sense. The initial distance that the mass slid was 1/3 of a meter. Then 13 centimeters is the final distance as the spring is compressed. So it is good that we made sure to take into account the extra height that the mass fell as it moved downwards. I'll leave it to you to make sure that the equation we got as an answer to number 64 is dimensionally correct. Thanks for listening.